gap between industry and academia. To guide us through this significant topic, we are honored to have with us Mr. Saravanabhavan Chandrasekar, engineer at QMax Systems. Saravanabhavan Chandrasekar sir is an electronics and embedded product development professional associated with QMax Systems, specializing in high-density PCB design, embedded hardware, firmware, and end-to-end electronics product engineering. With experience spanning industrial automation, IoT, IIoT hardware, telecom, medical, and automotive electronics, he contributes strong industry side expertise in converting concepts into manufacturable products, handling hardware design challenges, compliance, prototyping, and system integration. Though his profile reflects deep practical engineering experience rather than academic research or publications, he brings valuable insights into real world IIoT product development, industry expectations, and skill gaps seen in graduates, making him a suitable industry practice representative for discussions on bridging the gap between academia and modern IoT engineering requirements. With great respect, I invite Mr. Saravanabhavan sir to take over today's session. Sir, please.
Good morning, good evening, everyone. Very happy to see a lot of people. Generally, we don't have a lot of people in our meetings and conferences. So let me introduce myself. I'll just share the presentation. I think I can share the screen. So today we will discuss about industrial Internet of Things. So my name is Saravana, and I'm going to switch to another presentation to introduce what I do. That will give you a context on how it is relevant to the industry. Hope you are able to see the screen, right?
Yes,
so
sir.
you're
Yes, sir.
the screen. Okay. So I'm an electronics engineer. 37 years of experience. I started pretty early, and I'm more in the hardware space and bringing full product to production. So you can see something like a computer motherboard or an industrial product, something like that. Okay. So I will show you some of the product that will give you a context of what I'm doing, and that will also help in the gap between the industry and the academia, what we are doing actually. Okay, that's the idea behind it. So we are, this is what I do, end-to-end product development from concept all the way to manufacturing. So you might wonder what is all involved in a product development, right? So there's a concept validation, there's a hardware design. So I'll be more focusing on electronic products. Of course, we do a lot of mechanical related products also, but my focus will be more on electronics, hardware. That will give you an idea. It's more close to industrial IoT, and I'll also showcase a few industrial IoT products to give you an idea. So typically it starts with a concept, do the circuit diagram, do the PCB layout, also do signal integrity, power integrity, thermal, because these days the boards are high speed boards. You may need to do signal integrity, power integrity analysis, and PCB fab, of course, assembly, and we also need to put them in an enclosure, right? So we like to do industrial design to make sure the product fits into the into the enclosure, and it also usable. And comes the firmware development. So today, every product or most of the product has some sort of firmware or software running into it. Like take a small microcontroller or any application, like, if you take a camera, even you take a mouse like this, something like a mouse, this has a microcontroller and a program is running inside the mouse. So you will see a lot of firmware development work happens. If you take any product, like you have a microcontroller, we need to do the programming, or if it's a microprocessor, we also need to do programming, and taking all the way data to the next level, to the application level, or doing something in the cloud. So there can be multiple operating systems. It could be bare metal C, or TOS, or Linux, or Windows, or something high level operating systems, or something very low level operating systems. So this probably pretty much we all know. Then comes to the complaints. So interestingly, there is a gap in understanding. So I've met a lot of students and also colleges that they have a big gap in understanding the compliance. So when you make a product, it should meet some compliance requirements like safety and things like that. For example, so you make electric, say, tube light, for example, or an electric fan. You have to ensure that the electric tube light does not cause interference to other equipments, or it is not causing an electrical shock, or it is not burning out and burning the entire building, or it's safe to operate. Also, when you dispose, it should be safely disposed, and it should not contain toxic materials. It's called ROHS. ROHS is restriction of hazardous substances. So, for example, you have tube light may contain plastic parts or might contain solder. Sometimes it might contain lead. So the lead is heavy metal. It can cause a lot of poisoning if ingested. So when you dispose the electronics, it has to be safely disposed, or probably we'll have to design with this in mind to reduce the materials, hazardous materials. So some of these are stringent requirements depending on the application of usage. Say, for example, you are making a home appliance. We need to ensure that it does not cause interference and things like that. If it's an automotive equipment, we need to ensure it meets the safety requirements. Like, so for example, if you are doing a braking system, or if you are doing an electronic power steering for an automotive, so when you turn left, it should turn left. It should not turn right, even in case of a failure of an electronics, right? So typically, these are all controlled by electronics like microcontrollers, microprocessors, motor drivers, and things like that. For example, the power steering of a car. We'll have to make sure that even if it fails safely and it does not cause harm. If the power steering fails, it should be able to manually control the steering without much difficulty. This is also, for example, if it's a braking system, if the power brake fails, then you should be able to manually brake the system. So this safety have to be involved. Let me ensure the safety of the product. So different countries have different regulations. In India, we call it as BIS and WPC. In other countries like US, it's FCC, and Europe, it's IEC and CE. So just to give you a context on these complaints. Then you go to manufacturing. So when you go to manufacturing, there is quite a bit of a challenge. So all these, still the stages, you have engineers working on it. When it goes to manufacturing, there will be workers who may not be highly qualified, but they may be very highly skilled. But you need to ensure that they understand the product and they do the testing. Manufacturing should be easy to do it. So it's all part of the design activity, which is what we generally do. So this is my office. A lot of engineers are developing new products all the time. You can see I'm going to show you some products. Don't think I'm going to introduce a lot of things, but still some of the case studies I will show you that will give you a context what the industry is doing. So so this is a motherboard design we designed recently, and it is successfully completed a few days back. This is I'm sure you are able to see this picture. This is a motherboard used in server type of application. Okay, it's a multi-core, like 128 core processor, and you have a lot of DDR, high-speed interface, and things like that. Like you can see 25 gig Ethernet interface. So this is Wi-Fi access point used in the router. A Wi-Fi router used on top of street lights. You can see the picture of the street light here. This we use Qualcomm processor. This you'll have to a product like this have to withstand a hot environment, like it is fitted outside, and it should not be heavy, and it should not stick out antennas outside, and it has to be sealed inside, and heat has to go out, and it can be very cold or it can be very hot in the summer. It should still function. And you can see a lot of other interfaces on this to give you an idea. This is the layout inside the board. This is structural health monitoring system for aerospace application. So in aircrafts, you will see the wings bending while takeoff and while landing. And also the fuselage itself will expand a little bit when pressurized and depressurized. There's a constant stress on the airframe. Typically the airframes, they will discard after 20 years or so. And also based on the number of flying hours, number of takeoffs and landings. So this company came for us for a requirement to analyze the structural health. So we did this hardware which will do an analysis of the structure and report real-time structural fatigue. Okay. This will typically use sensors. This is our industrial application. This uses sensors, piezoelectric sensors, transmit and receive in one side and receive on the other side, analyze the metal fatigue. Basically, analyzing the metal crystal structure after fatigue. So we'll have to ensure that the fatigue is analyzed before any incident. So this is a 100 gigabit Ethernet board used in typical data centers. So power supply, RF power supply. So when you have this also used in manufacturing, want to clean the wafer in the semiconductor manufacturing, you know, you all know silicon wafers, and it has to be cleaned to few atoms or even zero atom dust. So molecular level cleaning. So this will do a plasma generation, and it can clean the wafer before and after processing. So for example, if you want to do a wire bonding, it needs to be cleaned. So they use it in semiconductor factories. So RF power source, 1 kilowatt RF power source, 13.56 megahertz. It's an onboard diagnostics device used in the automotive industry. This is a cyber security device used for security, like a firewall for small offices and industries. The switch fabric, I'm just going to skip many of them. This is a digital signage player. It's a software-defined radio application used for the military application by the Indian. This is used by the Indian Army for communication. This is again an interesting application. This is used as augmented reality to help surgeons to do a precise surgery. Basically, a body or a part is done a CT scan and created a 3D model, and the 3D model is superimposed on the body when the surgeon makes the incision or something like that. You can see the pictures. It's augmented reality. Using AI and augmented reality, you can superimpose on this device. These are all just, I'm skipping some of them. Automotive boards, a lot of automotive PCBs we have done. So this industrial design, when I say industrial design, you would wonder what is that industrial design. We need to make a product look and feel, and also ergonomics. It should fit in the hand, or it should be usable, and it should also have the interface in the right place, things like that. So so someone has to do it, and we do this all the time for the products that we develop. So some are industrial products, some are other applications. It has to look and feel should be very good. So coming to the IoT, so we did a recent project. We did a data center, huge data center in the US. So what we did is the power system, cooling system, and the hardware, and also the dashboard. So when you have a lot of devices, we need to integrate and use a dashboard for them. So this is a typical data center. You can see this. Okay, so the other point is this hydrogen fuel cell powered data center. In many places, you may not get power, grid power. The grid power may take a long time. So a company in the US started using hydrogen fuel cell to generate power, and that powers the data center. So we did the complete protocol implementation to interfacing with the hardware. This is a typical dashboard to give you an idea. So for example, we read power from multiple sensors and other data from multiple sensors. So each rack, you can see multiple racks. Typically, a data center will have multiple racks, and the computers are inside. Or, for example, your the familiar NVIDIA DGX servers are inside, and it will consume the power, and you can monitor all the parameters: temperature, humidity, airflow, and the power consumption on each outlet. So you can see a dashboard like this. You can see the power distribution unit. You can see different parameters. So this is a data center. It's a rack with multiple servers sitting in it. And this the left side, you can see a vertical big bars. These are all the power distribution units. The power distribution, power, it delivers power to the servers. So the power is also monitored, and the power is monitored and also can be controlled. This is an intelligent PDU, which means there's a lot of smartness on the edge. We'll discuss the smartness on the edge later as we go to the topic. So you see different sensors. You can see different industrial sensors. So typically you need temperature. Temperature is the most widely measured parameter, physical parameter. Probably, I think next comes weight, I guess. Temperature is one of the most widely measured parameter. So these days we are measuring air quality, to volatile material in the air, power consumption, and smell sensor, for example. So this is another case study, interesting case study we recently did for a Singapore-based company. There's a mandatory requirement by the Singapore government to monitor construction sites if they are causing pollution, like sound pollution, dust pollution, or any toxic gases or anything like that. Those things are monitored and reported to the government. I don't know if some of you would have seen in the news recently, there was a fire accident in a construction site in Hong Kong. It's a huge fire accident, probably the biggest one in Hong Kong history. So they were not monitoring certain
Excuse me,
things.
sir.
Yeah.
Sir, your PPT is obstructed with your video screen, sir. It's only for me or for everybody it is like that? I don't know.
So I'm sharing the screen. It says sharing. Sorry, others are able to see the screen.
I can see only the left part, the environmental monitoring system. The written part is being obstructed by the other screen. I don't know whether only for me it is like that.
Okay. Probably now we should see it. Is that right?
Yes, sir. Thank you.
Okay, I was sharing the entire screen. I should.
Thank you.
Okay, so you see a lot of these sensors, small sensors. So we did this complete project, and we are shipping several hundred units to them. And these are mandatory to be installed in construction sites. And so for example, this is a typical block diagram of an environmental monitoring system where you have multiple sensors connecting to this microcontroller, and then it's connecting to LTE and getting to the Singapore government dashboard. So they monitor the parameters. If there's a dust level is more, or any pollution level is more, or sound, for example, the noise level is high, they would ask the construction site to reduce the work or to stop the work. And also, it is more important for the safety of the construction employees. For example, the laborers will work on a building site. If there is a lot of smoke, dust, they may have a health hazard. So they want to monitor this and ensure their pollution levels are minimum in the construction site. So this is the IoT gateway we developed for the customer, the Singapore government. And this is a tilt sensor. This is another interesting one that goes into the construction site monitoring. So if you see construction, they dig a lot because they build a lot of high-rise buildings. And there are nearby buildings which can tilt with the digging on the sides, right? Or there's a compound wall, big compound wall that can tilt a little bit. So they asked us to make a device which will monitor the tilt very, very precisely. So they have put 1 degree, but it is like not 1 degree precision. It can monitor, even if it's a slight tilt for a prolonged period, it will monitor and it will transmit the data to the dashboard, and they can take a decision whether to stop the construction or to reinforce the compound wall or something that is tilting beyond the levels. So these are all the different sensors that went into it. So other case studies, I will just quickly go through. These are all industrial design case studies. Industrial IoT case studies. They want to control air conditioners for factories and commercial establishments. So this will control the air conditioner using a remote mechanism. And for example, Reliance showrooms are using this device. Cold room for monitoring cold room, This is splice detection used in the paper mills to detect paper splice or the joints while it's running at high speeds. Liquid level sensing for tanks. This uses a millimeter wave radar to detect the level in tanks. So this we did for ATEX compliant. ATEX compliant is, so again, I want to talk about the industry versus the academia. The point here is we generally don't look at the environment from a student point of it, like where these are used. For example, if the product is used in hazardous environment, or for example, a petroleum plant, or a gas filling, LPG filling station. So today we had an inquiry for a electronic product that goes into LPG filling stations. So there'll be a lot of fumes, LPG fumes. A small spark can trigger a big fire. So we have to ensure the device what we are making are ATEX compliant. ATEX compliant is an atmospheric explosive rating. So they call it as different zones. Zone 0 is most hazardous, or zone 1 is less hazardous. So we have also developed products for zone 0, where a spark in the air can cause a massive fire. So we have to ensure the product does not produce a spark, even a spark, when it is malfunctioning or things like that, or it should perform without a spark. So it's a cable tension meter. So small aircrafts, they use cables to control the control surfaces. So the control surfaces are like the flaps, rudders, elevators, ailerons. So this the cables control them. The pilot maneuvers the yoke. The yoke is connected to all these control surfaces through cables. You have to ensure the cable is of a right tension. So this device will measure the cable tension precisely. And this is deployed in at least 40 countries. This is one of the very successful products. The respiratory monitoring system, we did this for a very large research hospital in the US. This uses a small MEMS sensor to detect the lung sound. The lungs and cough sound are, the cough sound is of course very audible, but the lung sound is very feeble. So we need to make special sensors, special acoustics to capture the lung sound and record it. So later the doctor will download the file and audio and do a AI algorithms to find out if there is a disease. This has been done a year back. Now they're doing some patient trials with this product. Nanoscope to detect malaria parasite. They need to make a small, very, very small particles. We need to use a very, very high-end microscope. So we did this for a US company again. Okay, I will probably some of them. Okay, that's about it on my introduction. A second. So is the pace okay, or do you want to make it faster, slower? Or like and is the speed okay, or do you want to go a little bit slower? Or the context, is that okay?
It's okay, sir.
Okay, thank you. We'll go through another presentation. Hold on a second. Are you able to see my screen?
No, sir.
Okay. Okay. Switching to the screen. Okay. So we have off late, we have been getting a lot of inquiries for industrial IoT. And I want to touch upon this industrial IoT. So the fundamentals will focus on the fundamentals. I'll try to make it a little bit shorter. We'll focus on the fundamentals, how and what has happened in the past, and what is going to happen. Approximately, we can do a guess, but we don't know. And the core technologies, what is happening now, and also see what we can help to bridge the gap between the curriculum and
Sir,
the
the
industry.
presentation is not visible, sir.
Say that again.
Not for me.
Okay, is this visible? Okay, let me see this. Is screen visible? Is the screen visible now?
Now it is visible, sir. You have to hide that.
Okay, I will do that.
Okay, sir. Thank you so much.
So now it is visible, sir.
Okay, great, excellent. Okay, so we'll focus on the fundamentals, the core technologies. Again, also we'll see what we can help bridging the gap between the industry and the academia. That's one of the points. So I'll tell you a background. So from the industry, right, there is always a new requirement coming in. Also, we also need a lot of people. You can see Naukri, okay? For example. You can just go do a search on Naukri, you'll see hundreds of job openings. But at the same time, you see a lot of people, young and really good engineers, are not fitting the roles. Okay, so which means there's a small gap. We will try to address them and see what we can help from the industry side. I know the universities, the colleges, the people, the faculty members are struggling a lot to place the candidates, place the students in good companies. I understand the difficulty. I've been working with some of you. I know the pain points. Let's see how we can help. So going to this. So the industry 1.0 to 5.0. So basically, the industry evolved over a period of time. The first modernization, mechanization is a steam power. So once you get the steam power, people were not dependent on manual labor. They were using steam engines to do a lot of work. Particularly, they started with cotton mills to transportation and using steam engines. Later came the electricity. Once they have the electricity and motors became a major role in the modernization or the electrification, I should say. So motor is one of the most widely used machine. Is my audio clear, or do you want to move to a different place? There's a raining outside. If it is clear, just let me know. Or if you want me to move to a different place, I can do that. Is this okay? Is my audio okay?
Yes, sir.
Okay. Yeah, if it is too noisy, please let me know. Then I can move to a different location. If it is not a problem. So I should say, like, my father is also was involved in motor manufacturing and motor rewinding, repairs, all these things. But so the electricity and the motors are a very, very important role in the modern industrialization. So then the automation came in. Like, I started with a lot of connectivity to control and things like that. I started my career as a process control industry. Like, I was designing temperature controllers for steel plants. Way back in '88, I joined a company in Chennai where we were doing temperature controllers, temperature monitors, temperature controllers. Those days it was like more analog controls. Today these are all become a lot of digital, but we were doing a lot of analog controls. By then there were like PLCs coming in and others were also coming in. So I was also part of a couple of big projects, like the steel plant automation. There was like a Ultra steel plant, Eli steel plant. I was involved in, I mean, my portion was very small, but still, as a fresher, I was involved in some of the monitoring and control work. So then comes the current is called Industry 4.0, where IoT and big data are playing a major role. Like, we are monitoring, sending data to the cloud. We have solid, high throughput internet connection. So data is collected. We don't need internally. It's a lot of communication systems have been evolved. We have Modbus, we have Ethercat, we have Profinet, other high-speed interfaces. We can get a lot of data, process it, or monitoring it. Things like that are happening now. Probably later it could be more robotics. Probably now man is involved in this 5.0. So even now I've seen, personally visited factories in many developed countries and some in Asia. So they were almost 95% using robots for manufacturing. So I was in a factory a few years back. So everything was done by robots. The factory floor was dark because lights were switched off because there's no need for a human to interfere in it. But all these robots were working. When we went in, they switched on the light to show me the robots. So it's a lot of changes are happening. So interestingly, coming to the India, there's a production link incentives for Indian companies or companies in India for Made in India. So that's going to be a lot of opportunity for young engineers to work on this because of the government and government initiatives, and also because of the global unrest, I should say, not a big problem, a global unrest where things are moving from forest countries, probably Asian to South Asian country, like India, from China to India. A lot of things are changing. So we are also involved in many of these activities where, for example, Apple is manufacturing in India. They were in China, Taiwan. Now it's all getting manufactured in India. So there's a lot of opportunity for automotive, electronics, and pharmaceuticals. You can see a lot of pharmaceutical companies in India. In fact, we export a major pharmaceutical produce in India. So this the industry 4.0 or the industrial IoT will help enable this data-driven manufacturing, smart manufacturing, or using machines for manufacturing. The definition, I would say, is industrial IoT so focusing on machine-to-machine communication, big data, and collecting the data reliably and efficiently. That's the here. So you can see consumer IoT and industrial IoT. So for example, even in our office, we use IoT with switch on lights, switch off lights, control air conditioners, and monitoring and things like that. They use IoT. For industrial, it is for mainly for safety and efficiency. So industrial is like a mission critical, like for example, so if it's pharmaceutical industry or making a medical device, it should follow some process. And if the process is not followed or something goes wrong, there can be a major disaster. Like the medical equipment can go faulty, medical equipment go outside, or a faulty pharmaceutical product, like a medicine, can go outside without a quality check. So for example, if you're using vision-based checking or some other equipment to check the quality of a medicine or a pharmaceutical product or a medical device, today it's all, a lot of things are monitored by the industrial IoT vision systems and other devices. If it malfunctions or if it doesn't work properly, it can be a big, dangerous situation. So the key drivers, mainly to optimize power consumption, reduce downtime of machines, overall operational cost to keep the operational cost at minimum. So we can show some industrial case studies. I'll showcase some of them. Probably I'll tell you something as we go. Also, these days there are a lot of inspection using IIoT, or mostly vision-based inspection or other measurement devices. So it gives a clear record of the quality process. For example, we have a medicine or a product that's manufactured. We can use a barcode to read and have a name embedded on it or a number embedded on it, and keep tracking of the product. For quality and for safety, like so hazardous environment. For example, if there's a high voltage area, you don't want to enter into the high voltage area. So there's a barrier. So you can interlock using industrial IoT. Currently, they are using manual systems, keys to interlock. So these days, it is all getting in IoT devices to have an interlock system, or it can monitor the worker. So I've had a lot of examples, I would say. So there's a huge company in India, one of the largest company in India. They're making large steel tanks, huge steel tanks. The workers used to go inside the steel tanks and do all the welding and things like that. They want to monitor the workers' safety or the health of the worker. Probably in the huge, they enter into the tank, they do all the welding, and with the fumes or something like that, they might have painted, or they can get injured and they would have been inside it and nobody will know outside. So they want the safety, health of the workers inside a tank. And also other areas like where there are high voltage areas, they don't want people walking in without switching off the power supply. So we have implemented several safety systems like hydrogen leakage or toxic gas leakage detection system to worker safety. So the key drivers are efficiency, quality, and safety. So that's what drives the industrial IoT. Interestingly, we are in the right time in India, and we have a lot of qualified engineers to do this work. So you can see the stack, how the data goes to the cloud. So typically we have sensors, and we call it as the edge, almost the edge layer. We can get multiple different sensors, switches, actuators. Either it is for sensing or to do some activity, and it goes to the nearby server or nearby gateway, I would say, and it goes to the cloud. We will also discuss about why you should go to the cloud or do something locally, depending on the situation. So some cases we'll have to take the data to the cloud. Some cases we'll have to take a decision at the edge. So we'll discuss about the cloud or online or data at the edge. So by industrial IoT, I would mean regular IoT is for more fancy purpose, to reduce more comfort, whereas industrial IoT is like a very serious industrial application. So you can see the different layers. The edge layer is typically sensors, PLCs. They generate the data that is transported through the other interface, other gateway. So the gateway connects multiple sensors and sends the data to the cloud using protocols, probably HTTP or MQTT or other protocols. And the data is collected and processed again for different applications. They want to monitor quality, they want to monitor the worker safety, they want to monitor certain parameters, or they want to control certain machines or predict certain failures. So not all the cases we can do local. For example, if we want to do an analysis of a particular image, so for example, we are monitoring quality of a liquid, say a petroleum product. They do some measurements and they send the data to the cloud, where they have very big processing power to do all the processing. You don't need to have it at the edge. So they may be collecting data from 100 different locations and doing the processing in one place, mainly to reduce cost. But the other challenges are there. Some processing can be done locally or at the edge. So sensors are key. The first point to sense, I call them the eyes and ears. So that's what probably touch, I should say, like your hands. The process sensors, temperature, flow, like a lot of sensors are used currently in the industry, and it's going to be more going forward. We are using more these days. We are using a lot of complex sensors. For example, in one case, in many cases, we are using millimeter wave levels, for example, level You can use ultrasound or sometimes using radars, and also chemical. We have used spectrometer, using near infrared spectrometer for measuring certain parameters. Also in the food processing, we are using, in one application, we are using microwave to detect moisture level in food processing. And before it's getting processed, we want to monitor the moisture content in food grains, for example. So we were passing microwave and detecting the moisture content on the other side. Motion, again, motion and position, like you can see, we have the MIMS. So today I would say like the MEMS sensors. So we have the because of all the semiconductor technology improvement, there are sensor like gyroscopes, accelerometers. It's all small semiconductor devices. Even for the level sensors, we have AIP. AIP is antenna in a package. So the small IC will have antenna inside the package, inside an IC package, where it can transmit and receive millimeter waves. So these are used in, for example, detecting range or some object is moving closer. We can use this type of devices like a radar to detect, and also vibration for predictive maintenance. There's a product, motor is vibrating, we can detect. So numerous applications today, cameras are used, cameras and radars are used for safety and also for quality. As you all know, there are like autonomous vehicle that's moving inside the factory to carry materials from point A to point B. Now comes the electrical sensor. As we all know, a lot of sensors, mainly for voltage, current, power factor. So we have done hundreds or probably thousands of installation for the energy monitoring. So anything, for example, if you want to check the motor health. So motor is the most widely used machine. You want to check the health of a motor. So what you do, you measure the motor current, motor power factor, or motor temperature, motor vibration. So with this, you could detect a lot of issues on the motor, or even do a predictive maintenance. So the sensors are key. Every day there are new sensors coming up. And we are in the right time now so the industry itself is typically, it is a very slow moving thing, like unlike IT. So there has to be big machines to be made, and the sensors to be attached, and this has to be connected. So it is unlike you get a new mobile phone, you change it next few days. If there's a new mobile phone, you can change it. It is not possible with the industry. If there's a machine and it's in a big production line, you cannot just change one machine, or you cannot just change or just add a small sensor. It has to integrate with the OT. We'll look at that as we go. So when you say this sensors, the sensors have to be connected to a gateway. The sensors in a typical factory floor is, the factory floor is usually very big. So I've recently been to a factory here just a few days back. I went to a big factory, car manufacturing facility right here in Chennai. They wanted to take some parameters and display it. So it was not very easy to take a parameter from a PLC and display it. So the couple of big challenges are, so there'll be huge motors running. Okay? Sometimes a lot of motors running, contactors making and breaking, you can say contactors, high voltage switch gears, huge transformers. And all these are sheet metal enclosures and also sheet metal surfaces, right? So wireless communication becomes a huge challenge. And even wired communication becomes a huge challenge. If we have high speed, like Ethernet or things like that, they can also be disturbed by the noise that is generated by the electrical switch gears. Or, for example, there will be welding happening. It's a machine does the welding. The welding generates wide spectrum electromagnetic noise, so which could interfere with any communication. So you need to have a solid communication, a solid physical layer, as well as a solid protocol. So it should have a very robust protocol to handle the communication. So most of my work is involved with reducing electromagnetic interference on these devices. When we make a device, we have to make it electromagnetic noise immune, and also should make the device which radiates very less noise. That's what I do a lot of work throughout my career. So wired interfaces are reasonably well, working very well. Ethernet, serial communication, Modbus, basically RS-485. So now there's LoRaWAN and 5G are emerging. So in this case, the last week, I went to a big factory there, and there were multiple huge workshops, huge sheds, and they want to collect data from all the sheds and display them in the office. So we were thinking about using LoRaWAN, but still, because the entire building is made of steel structure, like, you can see the sheet metal or the steel sheets. So that makes like a Faraday cage, and the RF will not go out of the sheet. So we suggested them to use wired network. So that's, you can imagine a big car factory and they want to lay a lot of cables. It's going to be a big challenge. Let's see how it goes. IT with OT. Okay, so this is another basic thing probably we miss. So OT is like the operation tech, IT is information tech. Typically in a big offices, we connect all the data, like your computer being connected, your servers are connected, you have an internet, Wi-Fi, everything is working. And the products are quickly changing. Like you have a new laptop, you can change it. You have a new Wi-Fi router, we can change it. You have a new 4G to 5G, we can do it. But when it comes to factory floor, what we call it as an operation tech or OT, they use Modbus or very slow interface, or they use Profinet or Ethernet for timing synchronous. For example, you have a station of 10 robots or a state in a production line. They need to be synchronized to a few milliseconds or a few nanoseconds. So we use Ethernet where the timing is very determined, predictable. And so, for example, if you want to happen certain things in a particular second, it has to happen on a particular millisecond time frame. Whereas in the information technology area, like you give a command, the mail goes in a few seconds is still okay, or a few minutes is still okay. Whereas in the OT, in the factory floor, it has to be faster, or it has to be deterministic more than I should not say faster. It should be deterministic. Like when it wants to happen, it has to happen. You cannot reboot At the computer, like if you want to reboot, something happens, you just close the thing and open, right? So that's not possible in industry, where it will be a car coming out or a building is happening or something is getting lifted. It has to be synchronized. And interestingly, the products, life cycle of a product, so you can take a CNC lathe or a CNC machine, the life will be like 10 to 20 years. Whereas your laptop life is only 2 years, 3 years, or 5 years at the max. So here the technology is changing. Now we are trying to bridge between the operation tech and the IT. Like for example, so when we were there in the factory, we want to interface PLC to the office. They want to monitor the parameters in the office. So there's a two department. One is the factory floor and another is the IT department in the factory. So the IT department don't want to connect the PLC to their network. So the PLCs are old device. Probably they may not have the latest security updates and things like that. Whereas the operation tech, they don't want to connect their device to more vulnerable IT, where someone can hack the product, hack the network, and they can enter into a PLC, and the PLC, if it stops functioning, it could be a catastrophic damage. Okay? Or if it's a malfunctions, the machines can malfunction. Whereas in IT, something goes wrong, it could be a loss of money at the most, or a loss of business. Whereas you can imagine a PLC not sensing or not detecting a particular work, it could be a big disaster. So interestingly, they did not give an access. The operation tech, the factory floor, they said they don't want to connect their PLC to the information technology, IT network. The network is there in the company, but they don't want to connect the PLC to the network. The IT also said, no, we don't want to connect the PLC to our network. They don't have a security patch, something like that. So you can imagine the gap. Okay. So again, the important thing is the safety. When it comes to safety, I would say, like, you are developing equipment, or it could be a lot of things, right? So today we are even manufacturing aerospace products here, medical devices, military equipment. Okay, right now near Chennai, there's a factory for making weapons near Chennai. So they're making all the hand weapons. Imagine something goes wrong, and it could be a dangerous situation. So understanding the divide, understanding what is IT and what is both, using the same Ethernet, for example, Modbus over Ethernet, or your whatever HTTP over Ethernet, whatever it is, right? So the convergence, now we are connecting the PLCs to the ERP system. Now you understand what is an OT and what is an IT. So we need to somehow get the data to the shop floor, to the office, to control many things, to buy materials and stuff like that. So these are getting connected. So there's a lot of work going on. So the protocols, MQTT is the most simplest, easy protocol to publish or to get the data to the server. It says WhatsApp of the IoT. It's very easy, fast. You can subscribe to a particular activity or a particular device, and that gives you consistent data over a period of time. And the Modbus is a pretty old protocol, 1979. You can see a lot of devices with Modbus. They can be connected to a lot of devices, but you still want to connect to a different device, it's a problem. So now recently there are the newer interfaces, I would say, the OPC UA, the universal translator. So now, as I said, there's an old machine like a CNC lathe, and there's a new Wi-Fi router or a new Ethernet router. So how do you connect them? So you need to have a device or a translator, or they want to have a standard protocol. So today they have come out with a standard. They want to do a standard protocol between multiple machines. So, and there's a IO link is also a standard, a new standard for connecting devices. So I want to talk about a standard for a couple of minutes. I've been in this industry for almost 38 years, 37 years. Even before joining the industry, I was also working in other places on my own during my college days. So they say there's a standard coming in. When I started my career, we were using serial port for connecting mouse. So you have a mouse here. They used to connect using a serial port. We were discussing about this, we should have a standard interface to connect printer, connect mouse, or connect other devices like a modem. Those days there were not many peripheral devices. Okay. So we were discussing, and they were talking about there's going to be a new interface that will be forever. It's going to be the standard. They said the USB is going to be the standard. Later, after some time, we saw the USB coming up, the big USB A type. Then after some time, I mean, the A is still there, but the speed has changed. And now we are talking about, earlier it was 200 or less. I think the USB 1 standard is 20 Mbps or something like that. Now we are talking about 10 Gbps or 40 Gbps on USB 4.0. So 40 Gbps, sorry, 40 Gbps on USB 4.0. So you can have full 4K video at a full rate without compression, like a raw 4K video from a camera can be sent through a USB interface. So the standards, we call it as a standard. Today it's a standard, but the standard itself will change after a while because of the new technology coming. So we started say 2G is a standard. Now we have 3G, 4G, 5G, and people are talking about 6G. And many of my friends on the high-tech industry are also working on the 6G technology. So the standards are there, but the standards are going to change over a period of time. But whatever it is, we need to understand the current standard at least. Mainly, this has to go to the students. Go a little bit. Ash. There's a protocol stack. You can something like OSI model. So you have a lower level physical layers like the Ethernet or the RS485, the physical media to connect between the devices or sometimes wireless. And there's a next level is the Modbus or Profibus or EtherCAT, things like that. And also taking the data to the cloud using different protocols like MQTT or HTTP or other protocols. So you can see different security level. We have TLS, DTLS, and we have protocols like TCP, UDP, and we have the high-level protocols. You can see the different layers here: physical network, transport, and application layer. And also have their own usage. Okay, so now comes to the edge. So today we are all talking about cloud computing, AI, AI on edge. So what happens when there's a decision to be taken quickly, and you have to rely on if you want to take the data to the cloud, what happens? So basically, the edge computing is the data is processed on the edge or near to the machines or near to the devices. So, for example, you measure a device and see, you do a visual inspection, give a infer the results and control the device. For example, somebody is entering into a hazardous zone and they should switch on the machine. So the decision is taken locally. There we use a edge device. The edge computing on the edge. So you have to take a decision on the local server or on the edge or close to the place where the devices are sitting. So why we should not send the data to the cloud and get it back and do it? So when you send the data to the cloud, it has to go through multiple uncontrolled paths. For example, you have to send the data to the cloud through a ISP. So, for example, here you have to send the data through the Airtel or a Geo network. So they don't guarantee the network latency and things like that. They can take more time or it can be faster. We don't know. Sometimes if it is later, then that's a big problem. And also data privacy. So many factories, they don't want to send the data outside and they want to control within local. And bandwidth, for example, it's a video. You don't want to take an entire video. There are thousands of, in some factories, they're using thousands of cameras to monitor quality control. So we don't want to send all the data to the cloud, which is a huge tons and tons of data have to be transferred and processed and send it back. Instead, we can take a decision locally and send only the inferencing to the cloud, or we don't even need to send the inferencing to the cloud. So it's super reliable to take an action at the edge. Sometimes it is expensive because you need to have in one factory in Coimbatore, we have installed edge computing. AI on the edge, they want to take a decision quickly, but they have a lot of NVIDIA boxes on each floor or each station. They want to take a quick decision and switch off the machine. In some scenarios, we collect the data and send the data to the cloud and we process it and send it. So it is not timing critical or it's not mission critical. You can send the data to the cloud. If it is mission critical, timing critical, latency, then it can be processed on the edge. Intelligent sensors. So this is a hot topic. So there has been, we at QMax or myself are involved in many of these activities. We have developed edge AI cameras to detect performance, to detect anomalies in the factories, and also run and also do predictive maintenance or predictive failure prediction, and things like that. And also sometimes for the safety and the privacy. So it has to be done locally. So, yeah, so this is, we all know this, AI is getting evolved faster week by week. One of my customers said, like, it's changing by week. There's a new technology coming up, new algorithms coming up. the machine, the new chips are coming up to do things faster, cost effective. So today we are using ourselves, we have used several cameras in industrial applications to monitor production, monitor parameters. So it's a, and also in electronic production, for example, I don't know if you have seen the AOI machines. So they call it as automatic optical inspection. So which basically looks at every component in a PCB, and it makes sure the polarity is correct, the solder joint is correct wherever visible. So it does a very, very fast checking. You can search for AOI. So cameras are used for multiple detection. Just before coming here to this presentation, we were working on a proposal to give medical monitoring, medical sample monitoring using camera, using AI. So there's an allergy test. There's a strip where your blood sample is kept on the strip. And the strip will have multiple bots which will detect the allergy, what item you are allergic to. So there's a bots coming up on the strip. So we'll have to monitor. This is coming in a production line type of thing where they keep it in an equipment. They do a lot of them just to be monitored. And we are developing a device to using AI to detect the allergy levels using camera. So if you want to call it as a machine. So digital twins. So I want to show you the earlier presentation. So this is a dashboard, or I want to call it as a digital twin. So whatever happening on the field is replicated here in the screen. So we are exactly seeing what is happening inside a data center. Right now, so I'm sitting in Chennai and I'm monitoring a data center across the globe, right in the US. So I can monitor the power measurement, how much power is consumed, how much hydrogen is consumed, and each and every node I can monitor. And this is to give you a context of what is a digital twin. We are taking all the data, sending it to the cloud, and we are monitoring here. So now we get a point of what is a digital twin here. Virtual replica, basically, and monitor the assets. So with the industrial IoT or with AI or with this, we can measure, predict anomalies or predict some things which before failure. So in this case, I personally myself have been involved in motor manufacturing, motor rewinding. Okay. So we understand it inside out. So when the motor can fail, when there is a bearing failure or fan not working, or there's a rotor bar damaged, Things like that can be predicted easily using multiple sensors. So we recently also we developed a product for a customer to detect vibration in motors. So we can attach simple vibration sensors, motor current, motor vibration using accelerometers, and also monitor the motor temperature and detect certain anomalies before it happens, and it can be communicated easily. You would say it's a concept called motor current signature analysis, MCSA, motor current signature analysis. With the motor current, you can say, for example, cycle by cycle. If you monitor the current very closely, you can understand a lot of problems that can occur in the motor. This is like using a stethoscope to listen to it, something like that. Motor current is a very, very important parameter. And yeah, of course, we have these new sensors to monitor the vibration and things like that. The latest sensors are, I'm not telling them there's new sensors. The new sensors are extremely cost effective. We can have a small sensor for 200 rupees to monitor the vibration motor. Okay, the sensor itself will cost only that much. So, and it can monitor vibration at very high frequencies as well. So again, there is robotics coming in. The cost of robots have come down a lot. There are new motor technologies, motor control technologies, because of the advancement in MOSFET manufacturing. There are new MOSFETs which are used in controlling the motors, the actuators. So, for example, if we have an arm like this, there are multiple actuators or the joint motors, I want to call. So these are three-phase AC motors controlled by a CAN interface, and there's a small motor controller inside. Typically, they give 48 volts DC, which will convert into three-phase AC and actuate the motor or rotate. So then there's a reduction gear to rotate it. So with the advancement in microcontrollers and the MOSFETs and the motor controls are becoming extremely cheaper. For example, you can see a simple BLDC motor fan in your home. Right? So these days we have BLDC motors. So this is something very close to a BLDC motor. This is a PMSM motors, and like a servo motor, basically it's a servo motor control. It's becoming very, very cost effective these days, and the computing for that is also very cost effective. You can buy a big, very powerful AI processor motherboard for like $200 and implement it very quickly. We can have optical vision inspection and things like that. So this is getting common these days. You can see multiple places people are using robots, and this is going to change everything. Cyber security, this is another, when you are connecting machines, right? This is a challenge. As I said, the IT team did not allow us to connect the PLC to the network. The PLC is a different piece altogether. But again, so we don't have a choice. We need to connect them to a different network that still connects to the cloud or connects to the Ethernet or to the internet, which means it is vulnerable for outsiders to hack into the system. The connecting OT to IT opens doors. That's the key thing here. So there are a lot of secure devices coming up and also secure protocol. HTTPS or MQTTS is coming like a secured protocols. So, do you have any questions on this particular section? Or I will quickly go to the next. I have like, how much time do we have? I have 10 minutes. Let me go to that section I have. This, so please bear with me for another 10 minutes and will take much of your time. There's a gap, as I said. We need engineers. You have engineers, but there's a gap in the skill. There's a demand and there's a competency gap. So we need to work together as from the industry, we are ready to help. From the academics, you are already in a big pressure to help the students to get to the industry. We work together. So this is the biggest challenge I face. So this is a very old philosopher, Chinese philosopher called Confucius. So he said, I hear, I forget, I see, I remember, I do understand. This gives a strong emphasis for practical training, which is extremely important. I want to tell you something very important. 99.99% of the work does not need to be new, need not be creative, need not be innovative. We have to work with discipline, with seriousness. And also we have to do something that is already done. For example, understanding Ohm's law. Don't need to be innovative. You need to know it very well. That's about it. You need to know circuit theory. You need to know electronic devices, which is invented, developed in the last 50 years, 100 years. Still okay. But we need to know that. But I see a lot of students trying to catch with the latest technology and forgetting the basics. So I will focus on the basics. I would say I'm just going to skip because of time. Experimental learning. This is what I want to do. I want students. So if you send students to us, we are going to give them very basic things. Unless they have not done very basic things, they will not be able to clear our interview. So we ask them to do like very, very simple circuits. Okay. You will not believe we have 500 engineers, 500 students walking in for interview, and we ask them to do power supply circuit. You will not believe less than 1% of them will be able to draw a power supply circuit. Less than 1.5% will be able to design a simple audio amplifier. Okay. So this has been done 50 years back, 75 years back, right? It's a very simple thing, or at least we can use a transistor and do a simple audio amplifier. People don't do it, students don't do it. That's a gap we face, we see. So that's a lot of requirement for engineers, but we want them to understand the basics. Of course, innovation is important, but the basics, then the innovation. They will have to do something on their own. Even if it is simple, a simple circuit is still fine. They can make 20 different circuits. If they're an electronics engineer, electrical engineer, they should at least do some simple circuits. They just start with Arduino or Raspberry Pi, or they just buy sensors off the shelf and do it. So I asked them, did you do any project? They will say, no, I've done using Arduino. I said, okay. I'm asking, did you do any circuit on your own? I said, so this is not with just a few people, this is with 99.9% of students. So you can use a lot of simulation tools. We have ANSYS, MATLAB, You can try a lot of things using tools. So we can help the faculty to do some internship here in our office. Probably a few of them for 4 weeks. So that will help them see what is happening in the industry. So the students are having an understanding gap. You will have to teach them with the basics, the regulatory thing which I was talking about, and also some ethics and the safety engineering. We'll go to the next one. This is what we need to do. So we'll see what I can help with this, anything specific, not just motivation, I would say. We have to do something, real training, and more than just motivation from the industry. I don't know, industry people are super busy. I also have a lot of work and I don't know how I can help. You can start with see how a product works. Probably take a mouse, for example, like here the mouse that you can see the computer mouse. You can ask someone to build a mouse. It's already there, but still building a mouse is not easy. It takes multiple disciplines. You can include computer science department, you can include electrical or electronics and communication department, you can include mechanical department, and if you have something else, you can still include them. You develop a mouse. For example, I'm just telling you, even if it is done 100 times, it's still okay to do it again. That's what you will learn, the basics. Probably you can establish an MOU, I think, most of the colleges doing MOU with industries. But once they do it, they don't turn back. And I stopped doing MOU with industries. Sometimes they come and ask for an MOU and they say, okay, they're very serious about it. And after 1 week, they all disappear. Okay. That's a scenario. I know you have the faculty members have a lot of challenges, more focused on the teaching and a lot of other work, but don't plan for interfacing with the industry. I understand the concern, but yeah, somewhere you can bridge the gap. The skills, I would say, to start with, they need to start with PCB circuits, simple circuits, simple Linux basics, C programming, and things like that. You can do some small changes to the curriculum. Interdisciplinary is what I want to always see. You can work with some small industries nearby and go to the industry, even if it is small, even if they're doing something simple, ridiculous, still it's okay. You can have a few engineers, students go there, help them with that activity or understand what it is. Even if the small industry is still okay. Don't think it has to be new, high tech. I think everything is learning for a student. And also make a joint product with multiple departments together. So probably you can also buy something like a small IoT device you can connect. So you need to buy some industry standard product and try it out. So we are ready to bridge the gap. I'm ready. So you need to see how people are interested in. So do you have any questions?